Hello everyone, welcome back to Real-Time Systems. My name is Renuka, Assistant Professor in Department of Electronics and Communication, Maharaja Institute of Technology, Mysore. So in previous class we have studied how a single reactor and when you take two reactors, how they are going to vary in operation and how the computer will control each and every reactor at a time. Okay. There you had manual as well as automatic, and how a computer should incorporate all the movements in a plant to get the end product, right? But there are certain the challenges that you come across when you're going for a supervision control systems. In supervision control systems, you have to adapt both human intervention as well as the computer interventions or the softwares to control the entire plant. Why? Because if you just leave human or manual operation, then what would happen? It will be tough for anybody to gauge what is the end of the process which is going to get over in reactor 1 and what is going to start in reactor 2. We have seen already, correct? And then if you just go to supervisor control, automatic, then you have to always rely on the system alone, okay? And you'll not be able to intervene and say that you have to stop this plant and the composition has to be changed, there should be some modification in the plant, in the kind of end product that we're going to get, okay. So then you need to have manual or the human intervention that has to happen in the supervisory control. So we have to have what is called as a mixed mode of operation where you have human as well as the computer intervention. So that's why you have what is called as a mixed mode of operation in real-time systems. So now let us try to understand certain drawbacks and how to overcome such drawbacks in real-time system today. Okay. So the challenges in sequential control. So the complexity in the process increases. We all know that from a single reactor in a plant. Okay, concurrent operation in the time scaling, correct? Time constraint is a huge importance because the reduced time and n number of products, that gives you a very good outcome, right, in any of the industrial applications. So complexity in the process increases, then complex decisions. Complex decisions is like when should we start the sequence, the new sequence, when should we start, okay, after the previous. So the time again plays a vital role here. So the decision making, the complex decision making, and that's why we have to go for what is called as supervisory decision, where human and computer have to intervene and come to some kind of an understanding. Okay, now the computer says that these are the operations that needs to be performed. Now let me stop at that. Let me take the opinion of a human, or let me try to give some option so that they say, yeah, you can go ahead. So there should be some kind of, the dialog box which say that, yes, you can go ahead, stop, end the operation, end the task. So these kind of interactive programming should happen in a computer, the kind of software that we write, so that human can intervene in a plant control, okay, and to get a very good product at the end. So minimizing ideal time, so that the unproductive time, what we call, so the duration between the the different kind of composition that you're going to add on has to be reduced, as I've told you earlier, so that it is, since it is a waste time, we call it as a waste time, unproductive time has to be reduced. When you reduce it, then the performance will become great in a plant. That has to be reduced. Then you have what is, I've just explained you about the mixed supervisory control, where the computer is programmed to carry out necessary calculation and to present its decision for confirmation or rejection by the operator, or presents a range of options to the computer operator. So operator gets a huge range of options, whether to start after 5 minutes, time duration, closing, and closing the program, ending of the task. So these are the options given by the computer control to human, so that he can intervene and so that there will be no damages which will happen in any of the plant. And there is an important note. In process control terminology, continuous feedback control is referred to as loop control or modulation control or DDC or a modern system. So here when we are talking about an important terminology like feedback control, what is a feedback? Some amount of output is fed back to the input. So there is a controlling in a plant from input to output, right? So that itself is called as a the modulation control, or you can just call it as a loop control, or in a which is usually adapted in DDC, that is direct digital controllers in modern era. Okay. Let us take an example to understand DDC in detail. So we have, if you can just see this block diagrams here, first you have a furnace, then you have a float bath, ribbon form and cools, then you have glass is annealed, then you have lathe, then you have inspection, cutting, then you have removal of plates from the line. So these are the blocks that you can see in a simple sequence loop supervisory control continuous system. So if you remember, we have dealt about what do you mean by continuous system. What is a continuous system? Where you are not going to stop the operation of a plant, you are not going to halt it, right? You have the raw materials, you have the production line which keeps on going. The only thing is you are changing the compositions as and when required, as per your requirement, correct? So the best example here is, this is sequential. If you see the block diagram here, it is sequential, it is happening one after the other. Okay. Sequential means there should be a batch, because you know that sequential operation will always support the batch processing. So one after the other, this is a kind of processing. So it is sequential. It is loop because after this it is a complete loop. It controls, okay. The controls the heat of the furnace, temperature has to be controlled in each and every stage of this operation. Then you have supervisory control, because for each and every step here there has to be supervision of the temperature, which is very important in this application, that is the float glass process. Okay. So this is one of the example for a continuous system. Raw materials, what are the raw materials here? We consider it as sand, powdered glass and fluxes, which are mixed and fed into the furnace. So this is a furnace where you have all the raw materials to be fed. Once you are feeding all the raw materials, then at preheated, so it becomes like molten glass flows through it and it gets refined. So there will be a molten glass. So now the raw material has converted to molten glass, and that will be sent through the out of furnace, okay, and then it will be refined. So now the temperature here, so now when we are talking about the supervisory control here, what are we going to control and monitor? We are going to monitor and control the temperature of the fuel, because if the temperature is very high, let us assume that the temperature in the furnace is very high, the raw materials that has to be fed should be immense, okay. So if you have optimum amount of temperature that has been maintained, then so in order to maintain the production line high, okay, you need to maintain the temperature in the furnace so that the amount of raw materials which consume will be apt, okay. Then you have forms ribbons on float bath. So now what happens, the next is, after the temperature is reduced, then it will be sent over a float bath where the ribbons, it's a ribbon of these glass, will be sent for cooling purpose, okay. So once that is done, again here while cooling, it maintains sufficient to run on the roller to avoid damages on the surface. So it is not just the end entity, but when it is moving on the cooler, what happens? There might be damages on the surfaces too. There could be bubbles, there could, if not properly maintained, there could be a disassociation of these glass because they are still molten level, right. So to avoid that, you need to maintain the temperature again at this level. So not just the furnace, but also along the line along the float bath. Then after that, it passes through a lathe to anneal. So annealing is nothing but again maintaining a temperature of the entire molten glass internally. So internally what happens, it has to cool down. Sometimes if you just happen to touch ash, you know, if you have wood, okay, you burn it. If you try to touch ash thinking that it might be not hot, it is wrong, right? Internally the temperature would be high, okay, you might end up getting hurt yourself, right? So here the same way, the exterior might look that it has, you know, cooled, but internally it will be still hot. So to ensure that, annealing is again nothing but providing a cooling effect or cooling the substance or cooling the molten glass to a perfect temperature that is required for the production of any other material. Okay. So this annealing is nothing but maintaining the temperature again after sending it through lay. Then cut up station will be adjusted here. So before that there will be inspection of you know, molten glass. Okay. So there will be an inspection to check whether it has completely cooled, not completely, how cool is it for the required temperature for which you are going to convert it to, either if it is a steel, then steel sheets, or if it is a iron sheets, iron foils, or if it is glass, then you have glass sheets, glass rods. So based on that, how has the temperature been you know, properly maintained. So that has to be recorded before it. So if there are any defects, then what will it do? There will be a sprayer which sprays off the unwanted, or you can say damaged, or which is not properly you know, which has a problem with their surfaces, will be sprayed, and then that portion will be eliminated. Okay. So first will be the inspection. After inspection, then the entire molten sheet will go through the cutting edges where it will be cut. The cut up stations automatically inspection, then fault are sprayed with paint, then cutter required, then the cutters are here at this end which will cut the entire section in the required sizes and shape, as and when you have different kinds of instruments that can be seen, because we have seen in the rollers, right, rolling mills, where you have pin cords that will be sent through rollers, and then you can you know, change the dimension. You can make it into thin sheets or thick rods based on your requirements. So here in this example, it could be thin sheets of glass. So automatic stacker lifts the sheets from the production line. If it's a steel, then it will, what will it do? Here the removal of the plates from the line, it will be, there will be a plenty of automatic stakers. So it will just take the entire bundle and pile it up. So this is like automatic stakers will be there. So automation here, which is again supervisory control, because once it is dealt, then it has to go for the next batch processing to lift the entire stack and place it out of the production line. So this is the best example for your continuous system, how you are going to implement, how sequence, looping and supervision control are actually adapted in this kind of a control system. So in a direct digital control, you have already learned about what is DDC and how is that, how did we evolve to a simple monitoring system to DDC in previous topics. So here what you see is in this block diagram, you have digital computer here. So here we are just considering one computer, okay, digital computer. Then you have a processor. Then you have multiple control lines. Can you see here? They are multiple control lines. Okay. Then you have set points. Set points are very important here. These set points will tell you what will be the temperature, what will be the pressure based on the plant. Okay. What will be the set points that you are going to choose for a computer to monitor and control in a processor. Okay. Then here you have measured variables. What are the measured variables from the processor? It is connected to the human and computer supervision. Human and computer supervision, because we need both operating, because we need more options to make this plant work efficiently. Okay. So we have process inputs here, we have process outputs, and this is the control system. This is a complete control system. This is a complete process. These are all control lines, what you can see, vertical and horizontal. So these are all your feedback. Okay, these are all your feedback loops. Now feedback loop is critical and it is reliable, right? Feedback loop is very critical and reliable, and several control loops. Colors here you can see there are several control loops here, correct? Control loops, correct? And it is connected to one single computer. So even if there is any fault in this event, okay, the plant will not be affected. Are you able to understand? So here you have event malfunctioning. If there are any variation in the set points, this at the processor inputs, it will only make this digital computer go to its standalone condition. Okay, it will not affect the plant. Okay, so event malfunctioning and failure. So plant is plant in safe condition. It will keep the plant in safe condition. So incorporating incremental change to the actuators. So here if you want the actuators to work, what should you do? The settings here has to not be more. For example, let us say simple example that you usually see in day-to-day life. Okay, if you're just a nuclear family, you have 2 children and husband and wife. So that is, and if you there is some festival in the home, and what happens? All are having food, and a mother cooks food for 4 of them. Okay, and that is very simple and easy, correct? Now let us assume if the same family has say about 50 invitees from out, and the same person has to cook for 50 members. It will not be the same food on the menu. You'll have multiple, you have many items that you have to actually, feed the others, correct? Or serve the others, fine. So what will happen? One single person doing all the work will become very tedious. Do you agree? Within that same short span of time, right? Because you want everything to be fresh and fine. Okay, so now if you just take the same scenario where a same person calls 2 or 3 of their relatives who can accompany them, so what will happen? There will be distribution of work, correct? So each person will be handed over 2 or 3 dishes to be served in the buffet, correct? So now what is happening? There is a sharing of this entire entity. Similarly here, the same example, if you take that example here, to incorporate incremental changes in the actuators. If you take increment, what is increment? Only a small variation could be adjusted. If you take multiple inputs and you're trying to actuate or control multiple valves, multiple controllers at the same time slot, it becomes very tedious and it might give you erroneous result. Malfunctioning might happen, correct? So now limiting the rate of change of actuator settings. So you have to limit the changes that happens in the settings. So you have to limit the number of, in the previous example, if your invitees are there, 50 are fine, but you need not cook say about 20 dishes. You can just concise it to 10, distribute it. So time sharing and the productivity will be very good. Okay, the taste will be very good. The same way here, if you limit the changes that are set in an actuator, you can just say that during this particular time span you have only this to be operated, or 1 or 2 valves are open, not all. You can't have multiple composition happening, and single computer can't handle all the control or set points at the same instant of time. It has its limits, right? So now that is how you can have what is called as incremental changes in the actuators and limiting the rate of change of the actuator settings. Okay, you have to limit it. So this is the best example to show how direct digital controllers are usually used with one single computer. Then as the invention of ICs began, okay, then what happened? You have invention of microprocessors and standalone system, again you have multiple processors there. So it is not just single computer. Now you have multiple processors which will take care of different activities. So there is a sharing of operation at the same stipulated time. Okay. So this is about the feedback loop of a direct digital controllers. So now when you compare with the loop control to that of analog control, we can just bifurcate them into two different headers and try to understand what happens to its cost, performance, okay, and the safety of the system. So direct digital controllers and analog controllers, what happens if the cost, large number of loops can be accommodated in DDC. Even one single loop in DDC could be a higher cost in case of analog unit. One loop is equal to a cost of an analog unit. So here it has number of loops will be limited, and then the cost will be very high in case of an analog system or controllers. Then you have performance. What will happen to the performance? Simpler implications, you have wide range of control algorithms, improved controller accuracy, and reduces the drift. So the production line, the outcome of the product will be controlled, and the number of the product that is delivered there will be greater when compared to that of your normal analog controllers. So here the less drift, you have reduced drift here, and the complex and complicated structures for a simple even for a simple operation. Probably you remember about how we have the pegs, correct, on a plug board, and it was a laborious process. So even to get one bit of data, so it is laborious, time consuming, and it is very complex in nature. Okay. So next you have what are the different applications of DDC. First, applied to single or 100 loops. If you just take a simple system, you can just have a single loop just like that of washing machine. If consider that as a real-time system, microwave ovens. So it is just one single unit and one controller is required. But you take an industry, the turbines in the boilers, you have more number of loops that are required to operate the n number of controllers that are required, okay, and more number of set points that has to be measured. A boiler control scheme is the best example to know how the real-time computer control is actually implemented. If you just see here, you have set points and you have finally to a burner at the end. Here in the boiler turbines, you have to have steam with a definite amount of pressure. So pressure of steam needs to be maintained in the boilers, right? So for which you need to have fuel. The continuous fuel has to be fed along with a small amount of air that needs to be added so that it will not have any environmental damages. So that's the reason we have this operation. We have what is called as pressure transducer steam pressure, and then you have pressure controller here, which is denoted by PC. This is a set point. What is a set point? To maintain the pressure of the entire steam, correct? So if you have to maintain that, then there is a bias station. So this station can be either automatic or it could be manual. If it is automatic, then there will be a signal which will be sent from the set point. It automatically controls and the signal is passed through the burner. Okay, it will be fed to the burner. If it is manual, then again a manual key has to be entered at the station to set, and then that will be transmitted, and then you have the fuel being dumped in the burner. So this is the two possible entities at the bias station. Either it could be manual or it could be automatic. So this will end towards two different heads. One is called a high signal selector and the other you have a low signal selector. There are two inputs for this, one from the automatic, another from your oil flow. So here if you see, there is an oil flow for high signal selector HI, and for a low signal selector you have one input from either the automatic or manual, and then the other input is from your airflow controller. So here it is oil for the high precision or high signal selector. For low, it is the air pressure. Okay. So now the output, so you have two inputs here and you have one output. This one output is connected, which gives a set point, and this, okay, and that set point is for a airflow controller. Okay. And then this airflow controller is mixed in a ratio unit called as an R, which is connected to a combustion controller. So here the combustion, where you are going to add fuel, okay, and amount of triggering happens at this combustion controller, and it will be in a ratio unit R, and that will be mixed in your airflow controller. Okay. So this becomes a set point for airflow controller. Similarly, if a low signal selector is selected, then we have this output being connected to oil flow controller. Here for high signal selector, you have what is called as a airflow controller. For low signal selector, you have oil flow controller, correct? So when we have low signal selector, then the output of this will be connected to an oil flow controller, where the amount of oil will be the set point, and then it will be sent to the burner. So based on the two, whether it is high signal selector or the low signal selector, here you have ratio of proportion. At this stage you have what is called as a cascaded, or it is a loop, isn't it? So you have two loops here, okay, 1 and 2. So there are two loops here, okay. So there are two loops in the system which are actually cascaded, and also it also operates in a ratio of unit, okay, where the amount of air that has to be mixed along with the fuel, and then it will be sent to the burner. Okay. So these two, this is mainly to show that how a boiler controller scheme is used, where you can actually set the pressure based on the ratio as well as the cascaded. If you just go to the previous slide, you can see here cascaded loop and signal added in the ratio loop will be considered. Before we could go to the next unit about what is the general structure of a feedback control configuration and the general structure of inferential control configuration, we have to just know what do you mean by inferential, feed forward, adaptive, self-tuning controllers. So these are the three headers that you are going to study in the next coming session. Thank you for your patience listening.